The moon deceives us every night. For thousands of years, we've gazed up at it, admired its glow, and recited poetry about the sea of serenity and the sea of clarity, yet we've only ever seen one side. Always the same one. The other half of our celestial companion has remained hidden from humanity since the very first ancestor lifted their eyes to the stars. Why? Because the moon is locked in synchronous rotation. It takes exactly the same amount of time to spin once on its axis as it does to orbit Earth, about 27 days. And throughout all of human history, we could never peer beyond that veil. We invented myths, wove legends, and imagined what might lie there. And when we finally did look, reality turned out to be stranger than any fiction. The far side of the moon isn't just a mirror image of the near side. It's an entirely different world. A world without the familiar seas, without the dark patches that form the face, the rabbit, or the woman knitting in the lunar glow. Instead, it's covered in scars, craters layered upon craters. It's the oldest surface in the solar system, bearing witness to the era when planets were still assembling from cosmic debris. There lies a colossal wound from an impact so violent it nearly split the moon in two. There, in eternal darkness, rests ice older than the dinosaurs. There is silence, true silence, unlike anything found anywhere near Earth. And there, perhaps, lies humanity's future. Before we dive deeper, if you're enjoying this journey, please subscribe and like the video. Every week, we uncover cosmic secrets that textbooks never mention. Don't miss the next episode. When humans first pointed telescopes at the moon, they mistook its dark patches for actual oceans. In 1609, Galileo Galilei observed smooth, low-lying plains and gave them romantic names: the Sea of Rains, the Ocean of Storms, the Sea of Clarity. Of course, there was no water, just solidified lava, ancient basaltic plains that had flooded enormous impact basins billions of years ago. But the names stuck, and those seas became the moon's most recognizable feature, the very patterns that different cultures interpreted as faces, rabbits, or women. Everyone saw something different, yet everyone saw the same thing, because the moon always shows us the same hemisphere. But what about the other side? For centuries, no one knew. There was no way to find out. Astronomers could speculate: maybe it was an exact twin of the near side, or perhaps it held an atmosphere, or even hidden civilizations. But all of it was pure conjecture. The truth remained beyond the lunar horizon, quite literally. Synchronous rotation isn't an anomaly, it's the norm for large moons. Most satellites in the solar system are gravitationally locked to their planets, thanks to tidal forces. Earth's gravity slightly deforms the moon, creating tidal bulges. These bulges generate a torque that gradually slows the moon's spin until it matches its orbital period, a process that takes millions of years but is ultimately inevitable. This gravitational lock snapped into place roughly 4 billion years ago, shortly after the moon formed. So when humanity emerged much later, we only ever saw one face. Because of slight orbital tilts and eccentricities, we actually glimpse about 59% of the moon's surface over time, but the remaining 41% was completely unknown. It wasn't just a blind spot, it was a gaping hole in our map of reality, a blank patch the size of Australia, hanging just 380,000 kilometers above our heads. And that void bred myths. In the 19th century, science fiction filled the gap. Jules Verne's From the Earth to the Moon sent heroes to the lunar surface, but even he didn't describe the far side, there was simply no data. H.G. Wells populated his moon with subterranean civilizations in The First Men in the Moon, suggesting life had retreated underground. Imagination rushed in where knowledge ended. Then came the space race. The far side became the ultimate symbol of the unknown, a metaphor for all that was hidden and unreachable. The Soviet Union and the United States raced to dominate space, first satellite, first human in orbit, first spacewalk. The USSR surged ahead, but the far side remained unconquered. To see it, you needed a probe that could fly around the moon, photograph the hidden hemisphere, and transmit the images back through the void. Simple in theory, but in the 1950s, it was nearly impossible. You needed precise navigation, a powerful rocket, a camera system that worked in vacuum, and a communication link across hundreds of thousands of kilometers. And the USSR dared to try it first. On October 4, 1959, a rocket lifted off from Baikonur carrying Luna 3, a tiny spacecraft weighing just 278 kilograms, packed with cameras, transmitters, and orientation systems. Its mission: swing around the moon, photograph its far side, and return the images to Earth. No one had ever done this. No one even knew if it would work. The trajectory was carefully calculated so the probe would skim behind the moon at minimum distance, then swing back toward Earth to downlink its data. No landing. No orbital maneuvers. Just a flyby, a snapshot, and a return. On October 6, Luna 3 reached the moon's vicinity and began photographing. It carried 2 cameras, one wide-angle, one telephoto, using actual photographic film, specially designed to withstand cosmic radiation and extreme temperatures. After each exposure, the film was automatically developed on board, a chemical process performed in zero gravity and vacuum, a feat that still seems astonishing today. Then the film was scanned, and the images were slowly transmitted to Earth, pixel by pixel, each one a whisper of data piercing through the cosmic darkness. When the first grainy images appeared in the control center, silence fell. Scientists stared in disbelief. The far side looked nothing like the near side. No seas. Almost no dark patches. Instead, craters upon craters, as if the surface had been relentlessly hammered for billions of years. Bright, battered, scarred. It was a revelation. Why was one side flooded with lava while the other resembled a battlefield frozen in eternal war? The images were low resolution by modern standards, but even then, one truth was clear: the moon is asymmetric. It has 2 faces, 2 histories, and that asymmetry demanded an explanation. Soviet scientists celebrated. They had seen what had been hidden from humanity since the dawn of time. They mapped the terrain, naming features like Mare Muscoviense, the only sea on the far side, tiny compared to its near-side counterparts, and massive craters like Tsiolkovsky and Giordano Bruno, with its brilliant ray system. But the real discovery wasn't the names, it was the mystery. Why did the near side have vast lava plains, while the far side was almost entirely cratered highlands? The first hypothesis: different impact histories. Maybe the near side suffered more giant impacts, punching through the crust and allowing magma to flood the basins. But that didn't hold up. The far side is more heavily cratered, not less. Second idea: crustal thickness. What if the far side's crust is thicker, acting like a lid that traps magma beneath? That made sense. Lava can only erupt if pressure can break through the surface. But why would the crust be thicker on one side? The moon formed as a single body. What caused this imbalance? Third theory: Earth's gravity. The near side always faces our planet, so tidal heating from Earth might have kept it warmer, making the crust thinner and more fragile. Plausible, but models showed tidal heating alone couldn't account for such a dramatic difference. Fourth possibility: different composition. Perhaps, during the Moon's violent birth, likely from debris after a Mars-sized protoplanet slammed into early Earth, the materials didn't mix evenly. Heavier elements sank on one side, lighter ones on the other, leading to asymmetric crustal formation. For decades, scientists debated these ideas, until new missions provided answers. The 1960s brought a flood of lunar exploration. The USSR sent Luna 9, first soft landing, Luna 16, first robotic sample return, and Lunokhod 1, first rover. The US launched Apollo, and on July 20, 1969, Neil Armstrong stepped onto the Moon. 12 astronauts would walk there, collecting rocks and deploying instruments, but all landed on the near side. The far side remained out of reach because there's no direct radio contact with Earth. The Moon itself blocks the signal. To operate there, you need a relay satellite, technology that didn't exist yet. Still, orbiters like NASA's Lunar Orbiter program mapped the far side in detail. And the asymmetry grew even more puzzling. 30% of the near side is covered in dark basaltic seas, but less than 2% of the far side. The breakthrough came from Apollo samples. The basalt in the seas was younger, 3 to 3.5 billion years old, while the bright highlands were ancient, 4 to 4.5 billion years old. So the Moon started as a uniform, light-colored crust. Later, giant impacts carved basins. Hundreds of millions of years afterward, magma rose from the interior and flooded those basins, but only where the crust was thin enough. Orbital gravity measurements confirmed it. The far side crust averages 50 kilometers thick, while the near side is only 30 kilometers, a 20 kilometers difference on a body just 3,500 kilometers wide. That extra rock was an impenetrable barrier. Impacts created basins on the far side too, but the lava never reached the surface. It cooled and crystallized underground. But why is the crust thicker on the far side? Here's the leading theory. The Moon was born from catastrophe. About 4.5 billion years ago, a young, molten Earth collided with a Mars-sized body called Theia. The impact blasted a ring of vaporized rock into orbit, out of which the Moon coalesced as a global magma ocean. As it cooled, light minerals floated to form the crust, heavy ones sank to form the mantle. But cooling wasn't uniform. The near side faced the still glowing Earth, which radiated intense heat like a furnace. That extra warmth slowed cooling, producing a thinner crust. The far side, exposed to the cold void of space, cooled faster, and formed a thicker crust. Think of pouring water into two molds, one in a freezer, one in a fridge. The freezer mold makes thicker ice. Same with the Moon. Later, when volcanic activity began, magma could easily burst through the thin nearside crust, but was blocked by the far side's thick shell. But there's another factor: radioactive elements. Uranium, thorium, and potassium decay and produce heat, enough to sustain volcanism for billions of years. And these elements are concentrated on the near side. So the near side had two advantages. Thinner crust, from slower cooling under Earth's glow. Concentrated radioactive heat sources. The far side had neither. So it remained ancient, untouched, and densely cratered, a pristine archive of solar system history. Every crater is a timestamp. Big ones mark catastrophic collisions. Small ones record debris from billions of years of cosmic chaos. And layered on top of each other, they form a geological book one scientists are still learning to read. One of the most remarkable features is the South Pole Aitken Basin, the largest impact crater in the solar system. 2,500 kilometers wide, 13 kilometers deep. Imagine standing at its bottom. The rim would tower higher than Mount Everest, and the basin would stretch from Moscow to London. This impact, 4 billion years ago during the late heavy bombardment, was so powerful it punched through the crust, exposing the Moon's mantle. Spectral analysis confirms, the basin floor is rich in olivine and pyroxene, mantle minerals, not crustal rock. This gives us a rare window into the Moon's interior, without drilling. And there's more, water ice. At the lunar poles, especially within permanently shadowed craters, sunlight never reaches. Because the Moon's axial tilt is only 1.5 degrees, sunlight schemes the poles horizontally. Deep craters remain in perpetual darkness, with temperatures plunging to -230 degrees Celsius. Nothing evaporates at that cold, not even water. So how did water get there? Two leading theories. Comets, ice-rich bodies bombarded the Moon for billions of years. Most ice vaporized on impact, but some drifted into cold traps and froze permanently. Solar wind, the sun emits protons, hydrogen nuclei. When they strike lunar soil, they can bond with oxygen in minerals to form water molecules, trapped if they migrate into shadowed craters. Both processes likely contributed. Missions like India's Chandrayaan-1, 2008, and NASA's LRO confirmed hundreds of millions of tons of water ice at the poles. This isn't just science, it's survival. Water can be split into hydrogen and oxygen, rocket fuel. A lunar base could refuel ships bound for Mars or the asteroid belt. The Moon becomes a cosmic gas station, not a destination. And the far side is key, especially the South Pole Aitken Basin, which straddles the South Pole. It offers water, mantle samples, and strategic location. It's also rich in helium-3, a rare isotope scarce on Earth but abundant on the Moon. Why? The solar wind has bombarded the lunar surface for billions of years, implanting helium-3 into the soil. Earth's atmosphere and magnetic field shield us, but the Moon has no such protection. Helium-3 is the ideal fuel for future fusion reactors. It produces massive energy with minimal radioactive waste. Just a few hundred tons could power all of human civilization for a year. Estimates suggest millions of tons are embedded in the upper regolith, especially on the far side, where ancient anorthosite highlands, not young basalts, dominate. But the far side offers something even more precious: radio silence. On Earth, we're drowned in electromagnetic noise, cell towers, TV, satellites. Even remote observatories can't escape it. But the far side is shielded by 3,500 kilometers of rock. No Earth signal can penetrate. A radio telescope here would hear only the cosmos. It could detect faint signals from the cosmic dark ages, the era before the first stars formed, and from the epoch of reionization, when those stars lit up the universe. These signals are redshifted into long radio wavelengths, blocked by Earth's ionosphere and drowned in human-made noise. On the lunar far side, they'd be clear. Proposals exist for kilometer-scale antenna arrays in far-side craters, thousands of small receivers working together to map the early universe, study dark matter, and maybe even detect alien civilizations. But to operate there, you need relays. China understood this first. In 2018, it launched Keiqiao, a relay satellite stationed at the Earth-Moon L2 Lagrange point, visible to both Earth and the lunar far side. That paved the way for history. On January 3, 2019, China's Chang'e-4 became the first mission ever to land softly on the far side, touching down in von Karman crater inside the South Pole Aitken Basin. Its rover, Yutu-2, began analyzing soil, confirming mantle-rich material, as predicted. It measured radiation, critical for future astronauts, and even ran a biology experiment. Cotton seeds sprouted, the first life on the far side, though they froze after 14 lunar nights. Chang'e 4 proved the far side is accessible. No longer terra incognita. China plans more. Chang'e 6 will return far side samples. Chang'e 7 will scout polar resources. Chang'e 8 will test in situ construction and water extraction. Meanwhile, NASA's Artemis program targets the South Pole, part of the same basin. ESA dreams of a lunar village. India, Russia, and private companies like SpaceX are all racing to the moon. This isn't the Cold War's symbolic flag planting. Today's goal is practical: resources, science, strategic positioning. The moon is a stepping stone to Mars and beyond, and the far side is the ultimate prize. But what about the myths? People often call it the dark side, but that's a misnomer. The far side gets just as much sunlight as the near side. Dark here means unknown, hidden, and that secrecy fueled conspiracy theories, alien bases, secret missions, ancient ruins. In reality, dozens of missions, from the USSR, USA, China, Japan, India, and Europe, have photographed the far side in high resolution. No structures. No pyramids. Just craters, basins, and highlands. If something artificial existed, we'd see it. Modern images resolve objects smaller than a meter. Strange shapes. Square craters. Straight lines. These are natural, impacts along fault lines, chains of secondary craters, fresh ejecta rays. The moon is a museum of natural history, not alien archaeology. Yet the myth persists. In Pink Floyd's iconic album The Dark Side of the Moon, a metaphor for human madness, in films like Transformers, Dark of the Moon and Iron Sky. The far side is a cultural symbol of the hidden, the mysterious, the repressed. But here's the truth: reality is more astonishing than fiction. You don't need aliens to make the far side captivating. A basin that ripped open the moon's mantle. Ice older than life on Earth. Silence so deep you could hear the echo of the Big Bang. Rocks that remember the birth of the solar system. That's real. And it's more wondrous than any myth. Studying the moon teaches us about all planets. Craters reveal bombardment histories. Volcanic flows show internal heat. Magnetic anomalies hint at a long-dead core dynamo. Gravity maps, revealing mascons, mass concentrations under basins, help us model planetary interiors. The moon's center of mass is offset by 2 kilometers toward Earth, another asymmetry. And deep below lies a small iron core, about 500 kilometers wide, partially molten, confirmed by Apollo seismometers that recorded moonquakes. All of this stems from that ancient collision with Theia. Isotopic analysis shows moon rocks are nearly identical to Earth's, which is puzzling, if Theia formed elsewhere. Did the impact mix materials so thoroughly that differences vanished? Or did both bodies form in the same region of the solar system? Samples from the far side's mantle-rich regions may hold answers. Looking ahead, the far side is central to humanity's future in space. Water ice enables long-term habitation and fuel production. Helium-3 could power clean fusion reactors. Radio silence offers unparalleled astronomy. Strategic location makes it a hub for deep space missions. But challenges remain. No direct Earth communication need relay constellations. 14-day nights require nuclear power or polar peaks of eternal light. Radiation exposure habitats may need to be built in lava tubes, though fewer exist on the far side. Psychological isolation. Earth is never visible. Rescue could take days. And there are ethical questions. Who owns the moon? The 1967 Outer Space Treaty bans national claims, but allows resource use. The US and Luxembourg now let companies own what they extract. But what if multiple nations target the same ice-rich craters? Who regulates radio-quiet zones near telescopes? The moon should be a global commons, like Antarctica. International cooperation, not conflict, must guide its future. Philosophically, the far side reminds us, half of reality is hidden until we seek it. For all human history, we saw only one face of our closest neighbor. Then we built a machine to look behind the curtain. That's the spirit of science. When you can't see directly, invent a way to see. The far side also symbolizes the unknowable future. When Luna 3 sent back its first images, scientists expected seas. Instead, they found craters. Likewise, our plans for space will surely meet surprises: alien life, cosmic dangers, new physics. Most importantly, the far side restores wonder. In an age when every corner of Earth is mapped and streamed, it's comforting to know that just 380,000 kilometers away, a whole world remains to be explored. A world where every stone tells a story, every shadow holds possibility. Humanity's era of terrestrial exploration is over. Now begins the interplanetary age. The moon is our first step. Mars is next. And the far side of the moon? It's not the end of the journey, it's the beginning. It was once hidden. Now it's revealed, but still mysterious. Because the more we learn, the more questions arise. How extreme is the asymmetry? What secrets lie in the mantle? How much ice is really there? Could life survive in shielded lava tubes? We'll only find out when we go there, and stay. And when we do, the far side will no longer be far. It will simply be another part of our world, a world that grows larger with every generation. Luna 3 took the first photograph. Chang'e 4 took the first step. What comes next is up to us. So the next time you look up at the moon, remember, you're only seeing half the story. Beyond the horizon lies a world of scars and silence, ice and ancient rock, holding the history of our solar system. And that world is no longer closed to us. We've glimpsed it. Touched it. Soon, we'll live there. The far side of the moon isn't a destination. It's a doorway. And through it lies the path to the stars. If you enjoyed this journey, like, subscribe, and join us next time as we uncover more cosmic secrets. Until then, keep looking up.